What do you mean minimize a functional? So, right, this is a function we're getting out of this thing. So we know how to minimize, right? How do we minimize something? I give you a function, you minimize it by saying, take a derivative. You set it to 0, right? That's what we've learned if we've learned nothing else about minimization. Set a derivative to 0. Oh, it might not be a minimum, it might be a maximum. By the way, there's no maximum error you can make here. You can make infinity error if you want, right? So if we find a minimum, if we find what's equivalent to the derivative being 0 for this function, this is going to be our solution that we want. There is no maximum, right? So remember in calculus, they always say, oh, your derivative is 0. Well, is that a maximum or a minimum? There's no maximum here, okay? So it's only a minimum. So what does it mean to take a derivative? This is where the variational part comes in. There's this idea of a derivative in functional space. And it's the following. That's the representation of it. This is like your derivative operator. This is like df dx. But it's not a function of x. It is, but it's through the function phi. Okay? It's a functional. And so if you write this out, and this is, again, this is calculus of variations, but who cares? Let me just write it down what this translates to. And then we'll talk about it. That's the definition of that variational derivative. You take this function f, which is a function of all of psi of x, psi, y, and you say, I will take d dx of df d phi dx. So I think of it, f as a function of this variable. Take the derivative and then take the x derivative. Function now of psi of y. And we'll see how this works out in a minute here. Then take the dy, blah, blah, blah. And what do I want to do to this? I want to set this equal to 0. Okay? And if I do that, I have a minimized. Okay, so that's the definition of, that's your generalization of the concept of derivative, setting the derivative to 0. Yeah?
So the cap f, will that be our governing function?
I'm going to show you what cap f is in a minute. So what I want to do is figure out how do I construct cap f so that when I do this and take this variational derivative and set it to 0, really what I have is back to this PDE. That's what we're going to do right now.
So, because that g in the surface integral may or may not be that g there that you're saying. You're
That's right. Let's call that cap g, different g. Sorry.
Okay, so the cap f and cap g will be identified.
Yeah.
Okay, and this definition of the df dp, that is calculation variations, and so that's well defined.
Yep. Yep.
Trust me.
You can totally trust me. I'm trustworthy. Sometimes. Yeah. So, if you've had calculus of variation, fine. Otherwise, it doesn't matter. Like, we're not going to make a big deal of this, right? Part of what we're going to do is just going to outline how you set this thing up. And then we're going to use it. But I want you to have at least an idea of how you would go around or go about setting up the finite element scheme. The finite element scheme is not representing the solution the normal way. It's writing it in an integral form. Then from the integral form, we're going to show you that it's just big giant ax equal to b. That's all I care about today, is that you can understand that there's ax equal to b here, right? That's what we're doing.
I'm sorry,
Yeah. Mm-hmm.
you have df dphi equals a whole bunch of stuff minus df dphi equals 0. So
Yeah.
you just move the df dphi 5, so 2 df dphi, or
No. These are different than that. This is delta versus partial. This is variational derivative.
okay, that's a different.
Yeah.
Okay, got it.
Yeah. Okay, let's construct it. So what I'm going to do is I'm going to say the following. I'm going to tell you right now that this integral, which is a function of u. So the integral, remember, is this construction of integrals that somehow convey information about the PDE. It's going to look like the following. 1/2 it's a domain now of 2 dimensions. We're going to basically integrate over this kidney bean. Okay? So you have dx, dy, and what my integrand is the following. P u of x squared plus q u of y squared minus r u squared plus 2f u plus boundary term s2 ds minus g2 u plus 1/2 g1 u squared. Okay. My claim is this is our PDE from 2 boards over in the integral form. And you can ask, well, how did you get that? How did I write that down? I'll show you how. So first of all, if you look at this here is my f. Now, what I'm going to claim is that f, what I'm going to do is say, okay, well, but the f was supposed to, I was supposed to get f by minimization, right? I was supposed to get f that it was supposed to satisfy some minimization principle. Here's the minimization principle right here. Okay? So I'm going to basically apply that up to here and prove to you that, in fact, I am not a liar and that I'm being straight up with you and giving you this. Okay? So my f here, right, is this integral term here. And what I'm going to do now is say, okay, let's go ahead and calculate this now, but it's no longer phi, it's u. Okay? And then you say, okay, so I got to do the following. I got to calculate the following. Oop, and a minus. That has to be equal to 0. Now we're in just 2D. Okay? Just calculate this. It's not so hard. Equals d dx. Take this function f. Take derivatives with respect to u of x. U of x is like an independent, it's like your variable. Where do you see u of x here? Not there, not there, not there. Oh, there's 1. So, squared. So what do? I get a, oh yeah, and don't forget that factor of 1/2 out here, right? So if I take the derivative of u of x, I drop down a 2 in front, I get u of x times a p. So p times 2 u of x. And there's that factor of 1/2. 1/2 times 2 is 1. Sweet. That's the kind of math I like. Oh, and I'm taking an x derivative of this thing, right? There it is. That term look familiar to you? Watch this. I'm going to make a squiggle. Squiggle, 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 squiggle. Squiggle matches squiggle, 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 squiggle. Nice. Okay, 1 down. Now let's go to this term, plus d dy. Now take the ui derivative. Where do you see ui here? Well, it's not there. It's certainly not here. Right there, same thing. 2q ui. Oh, but there's a factor of 1/2. 1/2 times 2 is 1. So what I get here is q ui. Ready? Bless you, bless you, bless you. Double squiggle. And did you guys ever do that? That's how I used to do algebra, work out algebra. Like when I got terms that matched, you have to, okay, anyway. It's my bookkeeping trick. I'm passing it on to you for free. All right? We got matches, and then see, you can say, oh, where's the squiggle? There's a squiggle over there, and then 2 squiggles. See? I kind of do that, okay? And then finally, minus the f du. Okay, so there's no u here. There's no u there. There is a u here. So I get minus r times 2u, but the 2 cancels with that 1/2, so I get just minus ru. Okay? There's also a u here. There's a half there. Half and that 2 cancel, so I get plus f. Okay. Equals 0. Couple things to notice. Minus times a minus is a plus, so I get an RU. Don't forget that minus is there, because that minus was times this f. I got a minus f, but if I move it to the other side, it becomes plus f. And now I'll make circle, and this will be double circle. And look at this. Circle, double circle. You see, I have a PDE here that is exactly that PDE there. So in other words, if I pick this as my integrand in that integral, this is a representation of my full PDE in integral form. I've integrated it up.